Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. GATE 2022 Chemical Engineering, Previous Year Questions and Solutions, Mass Transfer Part 2. In this video course, we will analyze and find solution for the following 4 questions in mass transfer. Question number 40, question number 50, question number 51 and question number 52. I would appreciate if you subscribe to the channel. It will motivate us to produce valuable knowledge content for your career progress. So subscribe now before you forget. In mass transfer part 1, we discussed 4 questions. In this video, we will discuss the remaining 4 questions with detailed analysis and solution. Question number 40. A fractionator recovers 95 mole% propane as distillate from an equimolar mixture of N-propane and N-butane. The condensate is saturated liquid at 55 degrees centigrade. The Antoine equation is of the form ln P saturated equal to A minus B divided by T plus C. The constants are given below. Assuming Raoult's law, what will be the condenser pressure? The Antoine equation for estimating the saturation pressure for the pure components at temperature T is given as ln P saturated equal to A minus B by T plus C, where P is in bar, T is in Kelvin. Using the given values of the constants A, B and C, first determine the saturation pressure at 55 degrees centigrade for the N-propane and N-butane from the above expression. For N-propane, LPN works out to 2.9228 bar. For N-butane, ln P sat works out to 1.7179 bar. From the above two values, we get saturation pressure of N-butane 18.593 bar and for N-butane 5.573 bar. Given in the problem is that 95% of propane is recovered as distillate. Hence, mole fraction of the components in the distillate recovered is xdn propane 0.95, xdn butane 0.05. The pressure of the condenser is computed from P equal to partial pressure of N-propane plus partial pressure of N-butane. So the P becomes 0.95 times saturation pressure of N-propane plus 0.05 times saturation pressure of N-butane. Substituting the values of saturation pressures calculated above, we get the condensate pressure P equals 17.94 bar. Question number 50. Two camphor particles of radii 20 cm and 5 cm far away from each other are undergoing sublimation in a stream of air. The mass transfer coefficient is proportional to 1 by square root of r, where r, which is a function of t, is the radius of sphere at time t. Assume that the partial pressure of camphor away from the surface of the particle is 0. Also assume quasi-steady state, identical ambient conditions, and negligible heat transfer. If T1 and T2 are the time required for complete sublimation of the 20 cm and 5 cm camphor particles respectively, the ratio of T1 to T2 is shown here is the figure of the two camphor particles undergoing sublimation. Both camphor particles, particle 1 and particle 2, are kept at identical conditions of temperature and pressure at which sublimation takes place. The surface concentration of particle 1 is CS1 and that of the particle 2 is CS2. The partial pressure of the camphor away from the surface is 0. That means Cs infinity is equal to 0. The data given is that the mass transfer coefficient K is proportional to 1 by square root of RT, where RT is the radius of sphere at time t. The time taken for complete sublimation of the camphor particles is obtained from time t equals total moles of particles sublimated divided by the rate of sublimation. The underlying concept is the rate of mass transfer of camphor by sublimation from the surface of the particle to the atmosphere. The rate can be expressed as K into A, concentration at the surface, minus concentration far away from the particle. Thus, the rate of mass transfer or the sublimation rate for camphor particles 1 and 2 is written as R1 equals K1A1 into CCS1 minus CC infinity. R2 equal to K2 into A2 times CCS2 minus CC infinity. The radius of the particle 1, R1, is equal to 0.2 meter. The mass transfer coefficient of particle 1 is K1 equal to C times 1 divided by square root of 0.2, which works out to 2.2361 C, where C is the proportionality constant. Similarly, the radius of particle 2 R2 is 0.05 meter. Hence, the mass transfer coefficient for particle 2 is K2 equal to C times 1 by square root of 0.05, which works out to 4.4721 C. Now, the area of the spherical camphor particles 1 and 2 are estimated as A1 equals 4 pi R1 squared, which works out to 0.5026 square meter. Similarly, A2 equal to 4 pi R2 squared, which works out to 0.010314 square meter. Since both camphor particles are sublimating under the same conditions of temperature and pressure, the vapor pressure at the surface will be the same. The concentration at the surface of particle 1 will be same as the concentration at the surface of particle 2. Also, given the partial pressure of the camphor away from the surface, C infinity is equal to 0. Hence, we can write the rate of mass transfer or sublimation rate as R1 equal to 2.2361 C times 0.5027 times Cs minus 0. Similarly, R2 equal to 4.4721 C times 0.0314 times Cs minus 0. The number of moles of particle 1 sublimated is N1, which is equal to volume times density divided by molecular weight, which equals 4 by 3 phi R1 cube times rho divided by m, which works out to 0.0335 times density divided by m. Likewise, the number of moles of particle 2 sublimated is N2 equals 4 by 3 pi R2 cube times density divided by m, which works out to 0.0005235 times rho divided by m. Given that T1 is a time taken for complete sublimation of particle 1 and T2 is a time taken for complete sublimation of particle 2. Now we can estimate the time T1 as T1 equals N1 by R1, which is equal to 0.0335 times rho divided by m times 2.2361 C times 0.5027 times Cs. Likewise, T2 equal to N2 by R2, which equals 0.0005235 times rho divided by m times 4.4721 C times 0.0314 times Cs. The ratio of T1 to T2 works out to 8. Question number 51. A countercurrent absorption tower is designed to remove 95% of component A from an incoming binary gas mixer using pure solvent B. The mole ratio of A in the inlet gas is 0.02. The carrier gas flow rate is 50 kmol per hour. The equilibrium relation is given by Y is equal to 2x, where Y and X are the mole ratios of A in the gas and liquid phases respectively. If the tower is operated at twice a minimum solvent ratio flow rate, the mole ratio of A in the exit liquid stream is shown in this figure is a sketch of an absorption column with the data given. The inlet gas mole fraction of component A is 0.02. With 95% recovery, the mole fraction of A in the exit gas stream is 0.001. The carrier gas flow rate is 50 kmols per hour. The minimum liquid flow rate is that at which the outlet concentration of the liquid flowing out of the column is the maximum in value. The maximum concentration X max is the concentration of the liquid which is in equilibrium with the inlet solute concentration of the gas mixture flowing into the column yn plus 1. This figure illustrates how the liquid flow rate is determined from the equilibrium solubility plot and the specification data provided for the design of the absorption column. From the gas inlet concentration, draw a straight line such that it cuts the equilibrium curve at point O. And this point on the equilibrium curve represents the maximum liquid concentration point. The liquid concentration equilibrium with the inlet gas concentration. Since the liquid concentration of solute at the column inlet is 0, the gas outlet concentration Y1 on the y-axis indicates the operating point. Connect this point Y1 and the point O on the equilibrium curve. The line obtained is the minimum operating line. The slope of the minimum operating line is L by V minimum. At minimum operating line, you need infinite number of stages to achieve the given degree of separation due to pinching. There is no driving force at point O. So the actual line is decided by selecting a point P on the line connecting the outer concentration Yn plus 1 and the point O. The line connecting the gas outer concentration point Y1 and the point P is the actual operating line. The slope of the minimum operating line is obtained from Yn plus 1 minus Y1 equals L by B minimum into X max minus XO. The expression for the equilibrium line is given that y is equal to 2x. So the equilibrium line is a straight line with a slope m equal to 2. Given that Yn plus 1 is equal to 0.02, we get X max as Yn plus 1 divided by 2, which equals to 0.02 by 2, which works out to 0.01. Now substituting the values in the expression, we get the minimum solvent flow to gas ratio 0.02 minus 0.001 equal to L by V minimum times 0.01 minus 0. The minimum solvent to gas ratio is 1.9. It is given that the actual solvent to gas ratio is twice the minimum ratio. So the L by B actual works out to 2 times 1.9 equal to 3.8. Now we can write the expression for the actual operating line. 0.02 minus 0.001 equals L by V actual times Xn minus 0. Substituting the value of L by B actual equal to 3.8, the exit liquid concentration of A Xn equal 0.005. Question number 52. A binary mixer with two components A and B is to be separated in a distillation column to get 95 mole % A as the top product. The relative volatility for binary mixture alpha AB is 2. The column feed is a saturated liquid containing 50 mole% A. Under usual simplifying assumptions such as constant molar overflow, negligible heat loss, ideal trace, the minimum reflux ratio for separation is This is a straightforward problem. Given are the following data. Feed is saturated liquid. That means the quality of feed Q is equal to 1. Feed concentration X of 50 mole%. Relative volatility alpha AB is equal to 2. The more volatile component is A. The distillate concentration of the more volatile component XD is 0.95. The limiting condition occurs at minimum reflux ratio when an infinite number of trays will be required to effect separation. This occurs at a point where the rectification operating line intersects the equilibrium line. At minimum reflux, both operating lines touch the equilibrium line, that is pinch point, at y dash and x dash in the equilibrium diagram. You need infinite number of stages to effect separation. Given that the feed is a saturated liquid, that is Q is equal to 1. At minimum reflux, the Q line and the enrichment line both intersect the equilibrium line at the same point. Illustrated in this figure is the Mercaptelier diagram for designing the distillation column. Mole fraction of A in the feed is 0.5 and mole fraction of A in the distillate XD is 0.95. We draw the rectification line such that the line intersects the equilibrium line at P x dash minus y dash. The slope of the operating line is Rm divided by Rm plus 1. At minimum reflux, the slope of the operating line for rectification is obtained from the graph Rm divided by Rm plus 1 equals xt minus y dash divided by xt minus x dash. Since the feed is a saturated liquid, Q is equal to 1 and x dash is equal to xf. Substituting this at the minimum reflux, the slope of the rectification line becomes Rm divided by Rm plus 1 equals xt minus y dash divided by xt minus xf. Now let us write the relationship between the equilibrium concentration and relative volatility for ideal solution. Ya is equals alpha AB into XA divided by 1 plus alpha AB minus 1 into XA. Find out the value of y dash by substituting in the expression the values of alpha AB, which is 2, and x dash is equal to xf equal to 0.5. You will get y dash is equal to 0.666. Using the calculated value of y dash equal to 0.666, find out the slope of the rectification line at minimum reflux using the previously given expression. You get Rm by Rm plus 1 equal to 0.631. So the minimum reflux ratio is Rm equals 1.614. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.